Welcome to our lesson on the squeeze theorem in calculus. We'll start by understanding bounding functions. Bounding functions help approximate target function behavior. They trap a function between two simpler functions. These are called upper and lower bounds. They are vital in estimating limits. Consider the function f of x equals sine x divided by x. We analyze this as x approaches 0. Let's show the limit of this function equals 1. We know -1 is less than or equal to sine x, and sine x is less than or equal to 1 for all x. For positive x, divide this inequality by x. Now, -1 divided by x is less or equal. This is less than or equal to sine x divided by x. This is also less than or equal to 1 divided by x. As x approaches 0, they approach infinity. Refined to 0 is less than or equal to sine x divided by x. This is less than or equal to 1 for small x. Apply the squeeze theorem here. 0 and 1 converge to 0 and 1 respectively. Therefore, the limit of sine x divided by x is 1. Next, the squeeze theorem is also called the sandwich theorem. If g of x is less or equal to f of x, and f of x is less or equal to h of x, this applies to all x near point A. The limit of g of x equals the limit of h of x equals L. Therefore, f of x's limit also equals L. Consider g of x equals x squared. F of x equals x squared sine 1 divided by x. H of x equals minus x squared. Find the limit of f of x as x approaches 0. Let's analyze. -1 is less or equal to sine 1 divided by x. It is also less than or equal to 1. Hence, minus x squared is bounded. It's less than f of x, which is less than x squared. The limit of g of x is 0. The limit of h of x is also 0. The squeeze theorem says f of x's limit is 0. Let's explore the graphical interpretation. Graphically, f of x is squeezed between g of x and h of x. As x approaches a value, all functions reach the same limit, L. Let's graph g of x equals minus x squared. Then, f of x equals x squared cosine 1 divided by x. Finally, plot h of x equals x squared near 0. Notice how they are symmetric about the x-axis. All graphs converge to 0 as x approaches 0. Now, let's discuss algebraic applications. Use polynomial expressions with trigonometric identities for complex function limits. Evaluate the limit of x squared sine 1 divided by x squared. Bound sine 1 divided by x squared by -1 and 1. Multiply through by x squared. Minus x squared is less or equal than x squared sine 1 divided by x squared. This is less than or equal to plus x squared. The squeeze theorem leads to a limit of 0. Now, consider trigonometric limits. Evaluate the limit of x sine 1 divided by x. The sine function is bounded between -1 and 1. Multiply bounds by x, resulting in minus x. This is less than or equal to x sine 1 divided by x, and it is less than or equal to x. As x approaches 0, both bounds converge to 0. Thus, the limit of x sine 1 divided by x equals 0. Finally, prove limits using bounding functions. Identify appropriate upper and lower bounding functions. These functions encapsulate the target function at limit points. Pause here and try solving. Limit of tangent x minus square root of 2x plus 1. Solution. Consider approximation near x equals pi divided by 4. Tangent x is close to x plus square root of 2 times x minus pi divided by 4. Tangent x minus square root of 2x plus 1 approaches 1. Let g of x equals x and h of x equals 3x. Note that x is less than or equal to tangent x, less than or equal to 3x. Both g of x and h of x limit to pi divided by 4. By the squeeze theorem, tangent x limits to pi divided by 4. Therefore, the limit of tangent x minus square root of 2x plus 1 is 1.